So, ich hoffe, auch online sind jetzt alle gut versorgt und somit starten wir in das Semmelnar im April. Vorweg einmal, wenn Fragen sind, gerne im Chat stellen, also für alle, die online sind, für alle im Raum, bitte nach vorne kommen zu einem der Mikrofone, damit auch online alle die Frage verstehen können. Wir halten es normalerweise so, dass man jederzeit Fragen stellen darf, also auch drinnen. Ich hoffe, das passt auch für dich. Okay. Wunderbar. Und damit darf ich auch schon vorstellen, Alexander Prokop, zurzeit an der Uni Wien, Institut für Geografie angestellt als Professor. Geologie, Entschuldigung. Und auch nebenher noch an der Uni Graz. Seit gut 20 Jahren wahrscheinlich jetzt im Schnee-Lawinen-Business unterwegs. Angefangen auch schon bei der Doktorarbeit, dass er mit Laserscanning gearbeitet hat, also Laserscanning und Schneedeckenobservierung und hat sich im Prinzip wie ein roter Faden auch durchgesetzt, sowohl über die wissenschaftliche Laufbahn, aber auch eben über die private Firma, die du gegründet hast, 2012, das Snowscan, ein Ingenieurbüro, was sich eben auch mit Lawinenrisikomanagement beschäftigt. Und ja, wir sind gespannt, was du uns sagen kannst, wie nah wir mittlerweile wirklich schon sind, dass wir über automatische Messungen Schneedeckeneigenschaften herausfinden können und wie gut es in 4D vor allem funktioniert. Gut, die Bühne ist deine. Danke,
Paul, für die Vorstellung. I will talk in English, so for the broader community that they can also listen to this talk. Aber ihr könnt ruhig Fragen in Deutsch stellen. Versteht das auch. As you can see, my talk is about laser technologies and how those can improve avalanche forecasting or also avalanche detection. And already in my PhD, as Paul said, thanks Paul, I already investigated laser technologies, and that was basically laser scanning. That's already started 20 years ago, and we moved a lot forward in this time. There's a really increase of technology. So the question of the day is, how close are we to measure snowpack properties in 4 dimensions? Because that's what is interesting for any avalanche forecaster. How is the development in time and spatially, of course? So I will try to answer this question today. But before, as OEGSL is a community, and you might be interested who is working on what, I show you the team. So everybody listed here did work in all of this, what I'm presenting. So first is we have a current research project at the Arlberg. It's called Our Snow Out. And this is basically with the research group from the University in Graz. And this is Stefan Muckenhuber, Thomas Gölles, and Thomas will have the next talk in April at the SemmelNar. So it will be interesting, and he will talk about this research project. So I will not talk too much, but that's already a teaser for next month. Then it's Birgit Schlager, Thomas Wallner, Christoph Geisberger, and Katrin Lisa Kapperer. It's a great team working on things I also present today, but also in April, then Thomas. Then we have the group at the University in Vienna. We are basically working on distributed acoustic and seismic sensing. And that's Professor Augustinetti from the University in Milano as well. Then Bernhard Grasemann, the cool professor from the Institute of Geology. And then the students, Benedict, Bernhard, Hayek, and Daniel Collino from Italy. And then we have the group working on laser reflectance properties. And this is 2 groups, one in Lech and also one in Svalbard. And this is the French team I worked already a long time with. It's a great team as well. That's Florian Tolle, Jean-Michel Fried, Eric Bernard, and Stefan Graf from Lech, and Florian Singer had a lot as well. And I will start with some data from Svalbard, and a lot of work Holt Hancock did here. He's now at NGI in Norway, and then Martin Graz, and in Tromsø I work with Nick Axelmith at the Universität there. So that's quite a big community, and thanks for all these people for the work they did, so I can present this today. And then, of course, it's also important, the funding of this project. This is mainly funded by FFG, the Austrian Research Promotion Agency, and a lot of people support us. I want to mention the Lech Bergbanen AG, where we do a lot of research. The research side I mainly talk about is in Lech am Arlberg, is the Monenfluh, who was there already. And then, of course, we have people from the laser companies that support us, and also, of course, equipment, Dynafit ABS and Supernatural, for example, and PEEP. So that's also important to move around in avalanche terrain to be safe. Okay, so why are we all doing this? And this, I want to start dramatic and tragic. This is an avalanche happened in Svalbard, in Longyearbyen, in 2015, in December, just short before Christmas. You see here a slope, and you will see a lot of night pictures, because there is no daylight in winter in the Arctic. So that's the reason you see here night pictures. You see that slope here collapsed, and it was quite dramatic. You see a lot of houses were destroyed, cars were destroyed, and of course it was before an unknown situation. So quite dramatic. We had 11 houses destroyed, cars, snowmobiles, equipment. Houses were displaced up to 80 meters down the slope. 9 houses were occupied at that time, and 25 people were inside. 10 people were buried in the snow, 4 children, and unfortunately 2 people died. So it was a very tragic avalanche accident. You see here an image what happened. So a lot of these houses, all of them were displaced down the slope, and it was basically good they were displaced, because the houses in Svalbard are built on poles because of the permafrost ground. So the energy could distribute a bit to the movement. So the house, most of the houses stayed in a good shape. So that's why only 2 people died. So that was quite a good thing about that. And this is the situation there. Here the red is actually the avalanche that destroyed all the houses. So you saw also in the first image, it's not a big area, and it had that large impact on destruction of the houses. So it was just a slope, and it is why it's a huge wind drift, snowdrift problem, because here is Adventine, it's a big valley, and a lot of snow can be moved into that slope due to the wind. And usually in Svalbard, it's not very, especially in Longyearbyen, there's not much precipitation. So you would never have a large avalanche only because of snowfall. So you always have a snow drift problem going here into the slope. And you see there has been another avalanche just the next winter. And so the problem was there's no hazard map was there in Longyearbyen. There were no permanent protection measures and no reliable snow depth data. Okay, so there was a lot to improve. So what we did, I was at that time a professor at the Univ, at the University Center there. So we bought this nice device. It's a laser scanner. You might know those things. A laser scanner is a nice tool. It's actually a simple measurement device. You have the laser here. It emits a laser beam that's reflected by the surface. And when it emits the beam, a very precise clock is started. It's reflected by the surface, travels back, and the receiver knows the time, the travel time, and as it is speed of light, sorry. We know the distance of this point in relation to where you stand with your LiDAR. And of course, you need to have a reflection of this surface, and snow is not reflecting in every wavelength. So usual laser scanners are usually 1,500 nanometers. You can't use those LiDARs because you don't have a reflection of snow, or not very much. So usually the LiDAR you need to use, they have around 1,000 nanometers, like 900 or 1,065. And the VZ6000 from Riegel, it has 1,064 nanometers, so it's a perfect measurement device to measure snow or ice surfaces. And the great thing about this LiDAR is it also measures up to, let's say, 4,000 meters, so you can scan over long distances, and that helps a lot in all geoscience applications. If you do a scan from the slope, it takes about 30 minutes. It's important information. I will go back later. And you can put the LiDAR, there's quite a lot of UAV applications now. You can put it on any car, on any mobile thing. Then you need to have a GPS, of course, that you know the position of the LiDAR, and also an internal navigation system when you have an aircraft or so on, that you know in what direction the laser shoots out, basically. And all our maps we use now are done with airborne laser scanning. So this is quite nice. And then we had the laser available, so we could measure actually the avalanche that happened 1 year later. Again, it was night. And in this way, it also released from up here and also up here. You know, here's the wind putting the snow up here. And the publication, the paper is from Holt. The graph I will present now is in this paper. It's a great paper to read. And so what you do with laser scanning, you scan the surface without snow or before an event, and then you scan afterwards, and you have a difference of DEMs. And here, that was just the snow height before. You see there's not much snow usually in Svalbard. And then you have, after the avalanche, the snow depth distribution, and then you can make a differential map. And it's maybe not so good to see, but here was the snow released. Here is still snow available. And then we had two avalanches going down into with that avalanches, two houses were destroyed, but happily nobody was in there. And then, of course, also this slope that already released the year before also collapsed. You can see it nicely here, and went down. So what is really nice is you really see, you can make a mass balance of the avalanche. And especially here for GT, you can have really good input data for dynamic avalanche models. So you can you know how much snow is released, you know how much snow the avalanche takes in the track, so how much snow entrainment you have, and then how the snow is deposited. So you have a design avalanche, you can really see how the avalanche dynamics work in this case. And that's good because in Svalbard, we didn't have any data before. The snow is different, so the friction parameters in the models have to be somehow known. And that's quite great to have such a design avalanche. And we actually did the modeling of the avalanche. 4 different institutions did it. We used SAMOS and RAMS and different models, and actually all of us came to a similar result, which was great because, of course, you need to do your statistics about snow depth. The return period is in Norway. You need to tell an event that occurs once in 1,000 years and once in 5,000 years. In Austria, you know, we have a return period of 150 years for the hazard map. So that's quite interesting to do that and not so easy. But yeah, we had got similar results, and then you have quite good data for doing such snow dynamic modeling, avalanche modeling, sorry, and to draw the hazard map afterwards. And this is a picture I want to show you. Of course, we also then suggested some protection constructions. And if you look at the snow depth distribution we have here, and then actually how the protection construction were designed, it is very much related to the measurement of the LiDAR. And this helps a lot to design protection measures. Of course, we have also here a snowdrift fence. I told you before that a lot of snow is transported by the wind into that slope. So that's how the situation looks now. And I think those measurements help a lot in designing such constructions. And this is an example from a paper we wrote about a snowdrift fence at Prokop, that's in the ski resort of Sonnenkopf, Klösterle, just on the other side of the Arlberg. And here we basically did the same. We measured the snow distribution, how the fences actually work and how the snow is distributed into the slope. You can see it here nicely, which of the protection constructions here are prone to be snowed in and so on. So we redesigned those snow fences up there. They were built like in the 70s, I think, and we could increase the safety for the people down in Klösterle, I think, significantly with accumulating snow where it's not dangerous. So in this case, the LiDAR measurement also helped a lot to see how the snow is distributed and helps to design those protection constructions. But you will say, okay, Alex wanted to talk about avalanche forecasting and not about how to position protection constructions. So then the new thing is now what we use for avalanche forecasting. The main issue is that this device here, it's great, but it costs about 200,000 euros. So that's, of course, too expensive to deploy just as an avalanche forecasting tool in ski resort or so. But the automotive industry helps us now because they want to have cars moving without any help of people. So they have a lot of LiDARs and radars they try to use that the vehicle can move safely. And one are those LiDARs, and they are much, much cheaper. So if we put such a LiDAR like here on the pole, it's quite nice because you can measure just with, it's about 2,000 to 3,000 euros, such a device. You have a spatial information about the snowpack. And the great thing about these devices as well is that they are very fast. So you can measure an area in seconds. So with this device, it takes like 20 to 30 to 40 minutes, depending on how large the area is you scan. So this is really promising, and we are not the only ones using that. Here, this is a slide from Stefan Muckenhuber, and you see he loves to present this, that in 2030 a LiDAR will only cost anymore $100. So that would be great, but let's see if that's really happening. But if it's that cheap, of course, you can deploy such a LiDAR on every mast you have. So that's not the big problem. And so we tested those LiDARs. And this is also a slide from Pia Ruttner-Jansen. She is also doing a great work on this at SLF. And she compared different types of such automotive LiDARs. And we used in the beginning the Auster OS2, and now the device you just saw on the mast is a Livox Avia. It's the same one Pia is using. And you can see already the wavelength is in the good reflectance range we need. And the range of the LiDAR, how far you can actually measure, is given here by 450 meters for the Livox and 350 meters for the Oyster. So that's why we also try to use this one, that we can cover a larger area, basically. And before we use the Oyster, and I don't want to talk too much about it because Thomas will talk next month about it, but this was in a mobile setting, so you actually can go around with this multisense sensor and scan whatever you want. But as you know about avalanche forecasting, you need more data continuously, so you can track the changes in the snow depth and so in time. So that's why we have the installation on the mast. And here, that's the slope in Lech-am-Arlberg. That's the Monenfluh. So we are here in the slope, and we measure with one LiDAR in this direction and with one in this. And you see the distance here is about 75 meters. So it covers here the snow cornice here. There's a lot of snowdrift going on in this slope. And here we have those blasting towers, and they release avalanches. So we also want to have information about the avalanches itself when they release. The good thing about this Livox LiDAR is also it has a non-repetitive scanning pattern, which means you start the scanner and it scans very fast. And the longer you scan, the more point information you get. So that the point cloud, the density increases. As you see, after 3 seconds, you have quite a good information about it. So let's see about the data. And unfortunately, it's not so great like the developer of those devices tell us, but that's normal because, of course, when you want to sell such a device, you tell the maximum range you can scan with those. But in fact, we see here of this area A, we see here we scanned here. This is the cornice. You can see this cornice quite well. But already here in the back, we lose some data. And this is because the incident angle of the laser is not as good anymore. So you lose information. This is here about 120 meters. So let's say this 75 meters you can scan well, and you see this here. You see here the point density here. The black points are actually the measurement points of the Livox LiDAR. You see here the cornice is good because the incident angle is also better here. But actually you can here measure basically about 75 meters up to 100 meters maybe. And the same here, the Livox pointing in this direction is the same here. These are just artifacts of the interpolation. So you also only have here the points going about 75 to 100 meters. So the conclusion is that you can scan just up to 100 meters, even though the developer of the Livox says it's 450 meters, which reduces the application, of course, significantly. if you have a low incident angle, so if you have a flat incident angle, it reduces a lot the chance of getting good data. So you really have to choose the position good, which is often a problem because now in the setting we have, you have seen this, we have a power there. So we don't use a battery, we have a cable there, so that's great. But if you need power, you need to think about a LiDAR is quite power intensive. And that's the good point is, if you put this Levox LiDAR on your measurement pole, it's much better than to have just a 1D snow depth measurement. That's still the case. So if we can measure every 5 minutes or every minute if you want, and if you can then see, for example, how the cornice is growing, if the snow is melting, if there's snowdrift in the slope and so on, it's a much better information for an avalanche forecaster than just a 1D measurement, of course, which we have now in all measurement stations. So that will increase the possibility for avalanche forecasters a lot, in my opinion, if it's applied more in the future, especially also for people in a ski resort, for example. They have to keep their slopes avalanche safe. So if they look up in the morning, they see, okay, oops, there was a lot of snowdrift overnight, more than we thought. They can, of course, blast or close the ski run or etc. So this is quite nice. But now we have the snow depth, and this is a slide I think we have from Michelini. He's doing snowpack modeling. I want to show this because where a snowpack model sometimes fails is on the surface, because there's so many things happening on a snow surface. There is rain, there's snowfall, there's different kinds of radiation, incoming shortwave radiation, outgoing long-wave radiation, incoming long-wave radiation. We have wind, we have erosion, we have many physical processes. So this is quite difficult for a model to resolve. While within the snowpack, of course, we have a lot of physical processes as well, but we have a kind of a known boundary conditions, at least with 0 degrees here and measured temperature here at the surface. So modeling what is within the snowpack is great or better, but at the surface is quite difficult. So, and therefore, we also use a laser to classify snow surface properties. And it's also a distance measurement at the same time. So it is quite great that you can measure the snow property right before snowfall, because then you know, is there a weak layer buried? So is there surface hoar is buried? Is it melt freeze crust is buried? Was there wind drifted snow that is buried? So that this is really good that you have this measurement at the same time. So the snow depth and a measurement of the condition of the snow surface. You see here, this is a different LiDAR we're using. It's a Luft LiDAR because you can just plug it in to a Campbell logger or any other logger. And here it's also in Lechamalberg, where here there is a north-facing slope. We use this slope to classify usually surface hoar here. And this is an installation on an Arctic glacier where you're more interested in runoff and melt of the snow. So this is quite easily possible with a solar panel. So this LiDAR, we reduced a lot how often it measures, because of course, measure any 10 minutes or every hour is enough in this case. It has a bit of a different wavelength. Unfortunately, it's 650 nanometers. The best wavelength would be 1,100 nanometers, because the reflectance properties in this wavelength for snow crystals is very different. So you can see better the snow crystals, but it's not on the market yet. So in the meanwhile, we have to use this one. How can we now classify snow properties? It's because when you send a laser beam on any surface, you have different types of reflection. So the most common reflection is a diffuse reflection when you have a rather rough surface. So it reflects in any direction back and you get the portion back to your device. But you have also specular reflections. It means when the surface is quite smooth, then you have a lot of specular reflection. So less of the energy of the laser is coming back to you, to your device. And then, of course, you have also absorption in the material itself of the light of the laser. That's usually when you have water, for example. When you have water, you don't get any reflection back. If you send a laser beam to a lake, you will not get anything back. So that is pretty nice. So the reflectance properties are also dependent on other things, which you can see here. So, for example, the incident angle. That's why we have this stable installations to keep the incident angle the same. So with a moving light, of course, you have different incident angles. So it's much more difficult. But these type of measurements are already done now for airborne lidars as well, because you have quite of a similar incident angle most of the times. So if you are able to neglect the other parameters that work on reflectance properties of lidars, you can actually know something about the material properties you are measuring. And that's what we use. And then the very famous is Warren's paper on optical properties of snow, where you learn that impurities or liquid water content reduce the reflectance. But you really have to have a lot of water that is very significant. And this is what we used first in the Arctic. So you see here, this is just different years when the snow melts on the glacier and then when the ice melts as well. You have here the snow interface, but this is just the snow depth measurement. But more importantly is here the reflectance data. And the reflectance of dry snow is quite high in comparison of wet snow, which you can see here. And if you have ice, of course, ice is more smooth. You already have less reflectance. And the lowest is of wet ice. We validated this, of course, with automatic cameras, which you can see here. This is always how it looked like when those measurements where this data existed. You also see here the temperature that happened, so that also correlates, of course, well. And you have often these days here, for example, let's say this data, this is a clear day. So actually the glacier, even though it has, let's say, +2 degrees Celsius, but because of the outgoing long wave radiation, the glacier surface still is frozen. So you have no melting at the glacier surface in this case. And this you can really nicely classify with the snow reflectance data. A year later, it looked like this, so very different. We had not as much melting in 2023. If I would show you the data of 2024, it was a horrible year in Svalbard for the glaciers. It was the most melting we ever had. But it's not included here. But what I want to show you is that you can really clearly see when you have the wet ice, you have the most runoff when there's ice. And of course, you have the wet snow days, you really have a lot of runoff. Okay, I'm very talked much too much. But for avalanche forecasting, this is more interesting. So if you want to use the reflectance data to actually classify the snow surface, you need also to have data from your other met station, like surface temperature, like humidity and stuff, because, for example, the signature of the reflectance of surface hoar and new snow is quite similar. So just because out of the data, it's difficult to tell. But of course, surface hoar is formed under complete other weather conditions than when there's new snowfall. You easily see it on your other data you have from your met station. So in this way, if you combine this and create an algorithm, you actually see if there is surface hoar right before snowfall or not. A melt freeze crust is very easy. You can immediately see it on your reflectance data because you have to have melting before and then refreeze it. And if there's an avalanche event hitting the pole, you also see it because then the incident angle is different and then you have a sharp edge. Of course, we validated this with field measurements of crystal size and so on. So yeah, the conclusion is if you have a met station, you can use reflectance data very nicely for classifying snow surface conditions right before snowfall, and that helps the forecaster as well a lot. And last but not least, I have to make this a little bit faster. I also want to show you another laser technology that helps us to detect avalanches. And this is also done here at the Bodenfluidlech am Arlberg. It's fiber optic, acoustic and seismic sensing. And here you basically can detect avalanches at night under all weather conditions because you have a fiber optic cable buried in the ground a little bit. And you send a laser, a continuous laser through this cable. And the laser reflects in the fiber optic cable, in fiberglaskabel, and the reflectance is known. And if something changes, the reflection in the cable changes, like for example, temperature, the reflection is changing. But of course, also if you have vibration, and it's very sensitive, it's increasingly used in the world for all types of seismic or acoustic measurements because the reflectance changes. So you exactly know where it is as well. And you have every meter basically along the cable, a seismic and acoustic measurement. And that's great. Usually you have one seismometer there and one there. And here you have really a spatial information. And as it is continuous, you can measure all the time, basically. You have special tables. Here you see the installation. We went out of the top station of the ski lift into the slope and see if actually the avalanches that release here on these nice blasting towers that go here actually reach the ski run or not. That's how it basically is used. And I will show the movie. I hope it's working. Yeah, now it's working. So you will see a blast here. You see, of course, the explosion on the whole cable. And then you will see here an avalanche going here. And also in the back, you see here the signature of the avalanche and here. And it's really nice to show you on the movie because you see the explosion along the whole cable. This is the cable. And then you can really see where the avalanches went down. And this is quite a good tool to warn and give real-time warning. And this is already used in Norway and in Sweden on roads and railways because there is already a fiber optic cable usually there. So you just have to come with your device and you can monitor this avalanche. And the nice thing is you see here the signature of the explosion along the cable. You have really a three-dimensional information because if you georeference the cable and you, of course, know the position of the blasting tower, you exactly know the travel time of the explosion. And this is what I want to show you here. So here's the cable. And then you see after a while the two avalanches. And of course, the sound is traveling different in the air and in the snowpack. And here, for example, you have guided waves in the snowpack, and then you have the acoustic wave in the air, okay? And that's, of course, different, yeah, because the density is different. And when you use that, and you know the position of the cable, you can also actually measure snow depth above the cable. It's not as accurate as with the LiDAR, of course, but it's still enough to see if there was snow released or not above the cable. So you see the avalanche traveling, and you also see an amount of snow that was released. So that is quite nice in real time. And so that we could show as well. The time series looks like this. And you can also differentiate between a dense flow, for example. The signature is a little bit different than if you have a powder avalanche. On the data, we just have a master's thesis on that, where we make it more visible than in this graph. This is already an old graph, but it is possible. And it is really nice. Here we see a natural avalanche. So this is the waterfall diagram you just saw before. And here just a natural avalanche was measured without an explosion. And this is quite nice because this is already in use now as a real-time warning tool. Those were the first measurements we did back in 2013 in Lechenwalberg, and it's great that it's now really used. And the reason why it's increasingly used now is also the price. When we started with this interrogator costed about 300,000 euros, and now we're down to 80,000 euros. Okay, so I close with the question, how close are we now to measure snowpack properties in 4 dimensions? Maybe I can open the discussion with this. Of course, it's always, as a scientist, related on what is actually the accuracy of the measurement. So we can measure snowpack properties in 4 dimensions, but it depends on how accurate is it, what is the time frequency, what we actually need for our application. We are very good, I think, with the new automotive LiDARs in the time frequency, not so good in the spatial coverage. The resolution, for example, of the measurement is great. So we make every 2 centimeters a point. I think this is great. And then for the application, of course, it's also a matter of costs, if we can apply it for avalanche forecasting or not. But I think the costs are really good, so we can use it in the future more often. But I'm, of course, happy to hear your opinion about it. Yeah, and as this is a community, I also want to show you an art project, something different in the end. The reflectance data of the LiDAR was also used in an art project of digital weaving. This is also in a theater play going to hang up. So there is also applications of laser things, not in science, but also in art. Great artist. She's from the Netherlands, but lives in Norway. And I thank you for your attention with this slide from the Arctic, of course. This polar bear decided to stay at our station for 3 days, so we were not allowed to go out. But it was nice to see him, how he lives. Of course, it's a protected species, so you have to look that he's fine. But yeah, that's also research life. And I'm also happy to support young people that are going to work on snow and avalanche related topic in their master's thesis at the university and so on. And that's why SnowScan supports OEGSL with 1,000 euros. That was it. Thank you. I think it was too long a bit.
Oh, just 5 minutes, but that's okay. Thank you, Xander, for this very nice presentation. And we got already the first question from the internet, from the chat. It's funny, the name is Besprechungsraum Latin America, whoever that is. How dense can clouds be for the LiDAR to still work? Also wie dicht darf die Bewölkung sein, dass LiDAR noch funktioniert?
Yeah, that's a good question, and that's also quite nice with the automotive LiDARs because, of course, if you have a LiDAR measuring over 4,000 meters, the rule of thumb is if you can see the surface, you can also measure it. That's a good way to know. So if you have snowfall, usually, and you still see your slope, you can measure it because some portion of the LiDAR still reaches the snow surface. If it's totally foggy and you don't see anything, also the LiDAR can measure. But if it's deployed on a pole like this, it's almost never the case that the LiDAR doesn't see the snow surface, so in a range of 10 meters or 20 meters. On the data from the poles, you can see if it's very snowy, we can only measure like 10 to 20 meters. But usually that's possible, also under harsh weather conditions.
Thanks. And now they revealed, and they have a follow-up. So it's Geoconsult Salzburg, hiding under Besprechungsraum Latin America. Wo und wie werden die Glasfaserkabel verbaut?
That's also a very good question. I went over the picture. So usually we bury it in the ground, a few centimeters. Usually you also have like pipes under the ground, like at roads or railways. It's quite sensitive. You just need to check how deep the snowpack is and how much you lose. But if it's an application with large avalanches, you will also see it also if the cable is buried 1 meter in the ground, for example. In our installation, it's just buried like 3 centimeters in the ground. Sometimes we even leave it on the surface just because we're scientists and we want to get the most out of it.
Thanks. Paul?
I have a follow-up for the first question. How is the behavior with snowdrift? Is it also because mono-inflow, I think there's a lot of snowdrift?
Yeah.
Does it strongly influence the measurement?
So,
second, also sunlight. So if it's really a sunny day up there,
yeah,
you see this also in your data?
So strong sunlight just reduces the reflectance a bit, but you still can measure it. That's never a problem with LiDAR. It's just a bit reduction of the reflectance because a lot of radiation in this wavelength is available at that time when you have a lot of sunlight. But so it's just the range is reduced for like 20%, I would say. But the snowdrift is a good question. So when you have looked in the installation, that the pole is behind the cornice. So on the other side, it would be a problem because a lot of snow particles are moved on the ground. But because we are in the leeward slope, you know, the snow falls quite smoothly, and then it's not a problem. But of course, if you have a lot of snow moving on the ground, then of course the accuracy is reduced. The LiDAR will still measure it, but it will possibly be not as accurate. In general, those is a good question. Those automotive LiDARs are not as accurate, of course, as the 200,000 euro device, which measures quite accurate. Those automotive LiDARs, you can measure in 100 meters about 5 centimeters accurate, I would say. This is already the most what you get. So you have to make a very stable setting. But yeah, we are experienced in doing that, at least.
Great. From the internet, there are 2 more questions. Florian Singer asks, do you see this application for small-scale monitoring to protect infrastructures or regions? Or do you think it will also have an impact on avalanche forecasting for the situation report for skiers?
Yes, thanks, Brian. That's a good question. So the range we have currently, as I said, is just 75 meters. So you can measure, of course, around one on the pole, but you can always try to measure in the position you want to have the most information if you can install something there, of course, if it's possible to install such a LiDAR. So the application really is, if you have a prone, is of course it's more a local measurement. So for a regional information, it's not the right tool. But if you have many, of course, then you get again the regional information. So I would say both, but of course, just like the guys up in Lech, for example, they're very happy to get an information every morning about how the snow cornice was growing and so on. So I would say you have to use it wisely, of course, to get the information you need.
I think you already answered a little bit the second question I have here. Pierre and Jules ask, wird der LiDAR in Lech operationell verwendet? So is there an operational use of the LiDAR in the ski resort of Lech?
Yes, at the moment it's semi-operational, but Thomas might talk more about it because it needs, the main issue about operational is that it's stable because the user wants to have the result reliable every morning, and we're working basically on that. That we get reliable snow depth data every hour or every so that's basically a software issue and a operational issue. It's not about the measurement itself. So at the moment I'm asked to tell them, but in the future it should of course be online and everybody gets the information. So it's semi-operational at the moment. Hi, Pia and Jules.
Weitere Fragen aus dem Raum?
Studenten in Graz haben vielleicht noch eine Frage.
I have another one. You showed us the picture from Monimflu, but you're positioning the cheap LiDAR right in the release area. So how is the tower, the mast foundation there? So it has to be really strong, I guess. So
yes, that's a good question as well, and we actually answered this with LiDAR measurements from before, because you have seen it's on a rock, and it's a huge rock sticking out of the slope, and usually we don't have snow there the whole winter, only maybe 1 meter or so on. So first of all, the snow creep is not too powerful on the pole itself. Then the pole is stick into 2 rocks, so there's a crack in the rocks, so it's drilled with a lot of good stuff to the rock, so that's very solid. And then also what your question, I guess, is if it's there is a slope above, so the avalanches usually go either left or right from the pole. So it's also not prone to an avalanche event itself that is destroyed. But of course, that can happen if it's a huge year, of course. But then you don't lose much, as it is not so expensive.
die Studenten noch.
Students are still sleeping.
Ja, it's Monday morning.
Mit einer Genauigkeit. 5 Zentimeter bei 100 Meter bei dem Automotive. Würdest du sagen, dass der Regel hat jetzt 6000 besser als 5 Zentimeter ist?
Ja,
Auf 100 Meter.
auf 100 Meter schon.
Aber auf Kilometer.
Dann nicht mehr. Aber ich würde sagen, bis ein Kilometer, ja, I switched to English again. So like in 1,000 meters, it's quite difficult to measure. I'm more accurate with the VSAT 6000, but it's possible if you do a lot of work on the stability and the correction of the atmosphere and stuff, then it is possible. But in 100 meters, it's for sure possible to measure. Like the usual noise in the signal is about 1 to 2 centimeters.
100 meters, also with the VC 4000.
Yeah, of course, or even with a 400, or yeah. Then it's even more accurate with the 400.
Vielen Dank, Sandl, für diesen wunderschönen Einblick in was schon möglich ist mit Laserscannen und für deine Mühen eine Wechseltasse.
Dankeschön.
An dieser Stelle auch vielen herzlichen Dank für die Unterstützung.
Ja, gerne.
Das freut uns und das freut natürlich alle anderen da im Raum auch und auch alle Studenten, die dadurch profitieren und eine Förderung kriegen, dass sie ihre Arbeit an internationalen und nationalen Kongressen und anderen Möglichkeiten vorstellen. Vielen Dank. Ja, bleiben noch 2 Ankündigungen zu machen. Wie der Xandl schon gesagt hat, nächstes Semmelnar am 7. April wird auch wieder zum Thema Laserscannen und Schnee sein. Wir haben den Thomas Gölles da, der uns zeigen wird, was sie im Forschungsprojekt RS Snow Out alles gemacht haben und die arbeiten auch mit diesen mit diesen Leadern, die aus der Automobilbranche kommen. Da sind wir schon sehr gespannt, was sie uns da zeigen. Und dann 1 Monat später, am 7. Mai, findet das jährliche Annual Spring Meeting, also die Generalversammlung der OEGSL auch statt, wo wir um zahlreiche Teilnahme bitten. Zum einen ist es auch für die ein bisschen weiter weggelegenen, günstig gelegen der Termin, weil da ist die Interalpin, also diese große Seilbahnmesse in Innsbruck, wo auch zum ersten Mal eine Konferenz für alpine Naturgefahren in diesem Rahmen stattfinden wird, die INAG. Also man kann das sicher gut kombinieren und kann die Möglichkeit nutzen, da eben auch zur Generalversammlung der OEGSL zu kommen. Und in diesem Rahmen wird heuer auch ein neuer Vorstand gewählt. Also bitte alle Mitglieder um Teilnahme, am besten vor Ort hier in der Hofburg oder zumindest online, damit wir genug sind, um das auch mit unseren Stimmen dann absegnen zu können. Gut, ich glaube, soweit von unserer Seite. Vielen Dank noch einmal und allen anderen einen schönen Start in die Woche.